Hey everyone, we're doing bonding in chapter 8. Okay, we're starting with Okay, we're starting with section 8.1
Types.
Hey guys, we're bonding in Chapter 8. Section 8.1 is types of bonds. And
job.
we have some definitions. Bond energy is the energy required to break a bond. Ionic bond is a bond between a cat. Erica, be quiet! And an anion, a metal plus a nonmetal. Bond length is the internuclear distance between two atoms. Covalent bonding is where electrons are shared between two nuclei. Lastly, polar covalent bond is a covalent bond where electrons are shared unequally.
Ionic bonding.
Ionic bonding forces. Erica cannot do this. The girls really wanted to try to help lecture, and Bonnie did a great job. Say thank you, Bonnie. Okay, here we go. So, we have an equation for the energy that holds two ions together, and this is our equation for the energy holding two ions together, where Q1 and Q2 are the charge of the ions. R is the distance between the ion centers in nanometers. We're not going to have to use this equation at all. They are cracking up behind me. But we will need this equation later on when we start talking about melting points of ionic compounds. So we'll come back to this equation in about 2 or 3 weeks, and then you'll need to know it. Okay, electronegativity, you probably remember this. That's the ability of an atom to attract electrons to itself. And we've got a chart here of the electronegativity of all the different elements. So we see as we go to the right in the periodic table, electronegativity goes up. And as we go down the periodic table, electronegativity goes down. So we are now going to calculate the difference in electronegativity between the following pairs of atoms. If you want to pause at this point, you can. Hold on a second. Or you can just keep following along. Okay, so here are our 3 sets of atoms, and we're going to calculate the difference in electronegativity between these. The answers are all here. All I did was look at the electronegativity values for calcium, selenium, bromide, and arsenic. You always take the absolute values when you're looking at electronegativity differences. Oh my gosh, these girls are crazy. And we see between calcium bromide, the difference is 1.8, calcium and selenium, 1.4, calcium and arsenic, 1. And when we talk about bonds, so the differences in electronegativity tell you how much ionic or covalent character a bond has. If the difference in electronegativity is 0, your bond is just a covalent bond. It's not polar at all. When your electronegativity difference is large, usually we talk about being greater than 1.7. We say the bond is ionic. And intermediate, we would say the bond is a polar covalent bond. As the difference in electronegativity decreases, the covalent character increases. And as the difference in electronegativity increases, the ionic character increases. So we can talk about how ionic or covalent a bond is. So now we're going to arrange 1 through 3 up here from most to least ionic character. Hopefully you see that number 1, calcium and bromine together, would be the most ionic character. And then number 2 here, the difference is 1.4. That would be a little bit less ionic character. And then number 3 would have the least ionic character because the difference in electronegativity is only 1.
Okay, so Dr. Udell went to the bathroom. Okay, bye.
Bye.
Okay, bye. Wait, we have to stop.
All right, so now we're going to get to, we skipped a whole bunch of sections. We're going to get to what is a favorite section for many students, Lewis structures. And we have our directions for writing Lewis structures. And we're going to do some practice with writing Lewis structures. So number one, we're going to do sulfur trioxide. So step one, we add all the valence electrons. Valence electrons are the outer electrons. So S has 2 S electrons and 4 P electrons. S has 6 outer electrons. O also has 6 outer electrons. Times 3, we have 24 electrons. Step one's done. Draw the stick structure. Always put the first atom in the middle. So here's our stick structure. And we're going to fill in octets on all the atoms except for atoms that have less than 4 valence electrons. These all have at least 4 valence electrons. Fill in our octets. Hopefully you remember how to do this. Now these electrons don't all necessarily exist. We're just trying to get to the right Lewis structures. Check if the number of electrons in step 3 and step 1 match. Step 1 was 24 electrons. And in here, if we count them all up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This is 26 electrons. That is too many. And our instructions say, if step 3 is too large, erase 2 electrons from each of 2 adjacent atoms. The atoms have to be adjacent to each other. I'm going to erase 2 pairs of electrons, 1 from each of 2 adjacent atoms. And I'm going to draw a bond between those 2 atoms. So I'm going to draw a bond between the 2 atoms from which I erased 2 electrons. Keep repeating until the number of electrons in step 3 and step 1 match. I now have 24 electrons, which is how many I'm supposed to have. I am done. Let's do another one. I have an ion this time. So with ions, we're still going to add all the valence electrons. If it's an ion, we add or subtract additional electrons. Nitrogen has 5 valence electrons. Hydrogens have 1 valence electron times 4 hydrogens. Now if I have a positive charge, should I gain or lose electrons? Hopefully you realize we lost 1 electron. So we need 8 electrons. I'm going to fill in the octets. Oops, nope. First I'm going to draw the stick structure. Nitrogen in the middle, hydrogen on the outsides. Fill in the octets on all atoms except for atoms that have less than 4 valence electrons. Hydrogen had only 1 valence electron. I don't fill in octets for hydrogen. Check if the number of electrons in step 3 and 1 match. 2, 4, 6, 8, and 8. We're good. I have forgotten one thing though. Whenever we have an ion, you must put brackets around the structure and the charge of the ion on the outside of the brackets. Okay. Let's do one more. XeF4. Xenon, 8 outer electrons. Fluorine, by the way, you can pause this and see if you know how to do it, if you want to go ahead and do it. Fluorine has 7 outer electrons. We have 4 fluorines. So we've got 28, and 8 is 36 electrons. Draw the stick structure. Fill in our octets. Count them up. And when you count these all up, you should get 32 electrons. But we need 36. It's not going to help to get rid of any electrons. This is that funny one where we have to look at step 5. If the number of electrons in step 3 is too small, it was too small, it was only 32 as opposed to 36. we add electrons as lone pairs to the central atom. And we add those lone pairs on the diagonal. We need 4 more electrons, so we will add 2 more lone pairs. Okay, let's do one more. Let's just do HF. So H has, and you can pause if you want to do this on your own. H has 1 valence electron, F has 7, so that's 8 electrons. I had already written HF, that's kind of humorous, instead of just the formula HF. This should just be the formula HF, not the stick structure. Okay, fill in our octets. We don't fill in an octet for hydrogen, but we do for fluorine. And now we're going to check our electrons. This is 8 electrons, and we needed 8, so we are done. Okay, section 812, resonance. Resonance is something that happens when more than one valid Lewis structure exists for a molecule. And the example that we are going to do is SO3, which we've already looked at. So SO3, we just did the Lewis structure, and we put the double bond on the right side. Now, you will notice that I could have put the double bond down at the bottom. Or I could have put the double bond on the left side. And we say that all 3 structures are equally valid. In fact, what is really believed is that the double bond is spinning and switching places between the right side, the bottom, and the left side continuously. So really what this would look like is this, where I'm not putting the outer electrons, the pairs on the O's in this picture. That double bond spends 1/3 of its time on the right, 1/3 of its time on the bottom, and 1/3 of its time on the left. So we have one bond, the one double bond, one of the bonds in the double bond is moving between the right side, the bottom, and the left side continuously. Notice there are 3 places that the bond could be, so the bond spends 1/3 of its time in each place. So the last section we're going to do today, oh no, there's 2 more, sorry. We're going to do resonance. And did I already do resonance? Oh my gosh, I'm going crazy. Sorry about that. You're probably laughing at me right now. I had a little break and I filled out section 8.13, which is the last section we're going to do today. Valence shell electron pair repulsion theory. This is what gives us our geometry for different molecules and lets us know what kind of geometry a specific molecule would have. Some of you loved this, some of you don't like it, but this is what we're going to be doing. So first you have to learn some terminology. Steric number is the number of bonded atoms and lone pairs on a central atom. Some more terminology. These are things you're going to see in a little chart below. In the chart, X means an atom, 2 dots means a lone pair, an open triangle represents either electrons or an atom coming out toward you. And if you see something that is in the form of a triangle but it's a bunch of lines, that means the atom or lone pairs are going behind the screen that you are looking at. All right, so here is our chart. Different geometries. Down the left side is steric number, lone pairs plus bonded atoms. And going to the right is how many lone pairs are on the central atom. So if you have steric number 2, no lone pairs, you're going to be linear. Steric number 3, no lone pairs. So 3 atoms, no lone pairs, trigonal planar. Let's suppose we have steric number 3, two bonded atoms and one lone pair, that would be called bent or angular. So here's my two atoms, and here's my lone pair. Now the electron geometry, these are all molecular geometries we're looking at. The electron geometry would be, where are the electrons? And the electron geometry, can you see that that would actually be trigonal planar? So the molecule will be bent or angular, but if we look at all the electrons around the central atom, that geometry would actually be trigonal planar. In fact, this first column with no lone pairs, that's always our electron geometry. Electron geometry. And the rest would be our molecule geometry, if we do have lone pairs. And this symbol right here means we're coming out at the board toward you. This symbol right here means you're going behind the screen or behind the board. You don't have to use those symbols. We could just use straight lines. It's just trying to show you the three-dimensional picture of each different geometry. All right, we're not going to actually practice this right now. We will be doing this in class when we get to class next time. Okay.